Am I audible? Am I audible?
Yes, sir.
Can you see the screen?
Yes.
Sir.
Am I audible?
Yes, sir.
Am I audible?
Yes, sir.
Yes, sir. You are.
I can't hear you. Can somebody respond? Am I audible or not?
Yes, sir.
Okay. Somebody said yes, yes, yes. Okay. Yeah. When you are not able to see the screen or anything, please let me know through the WhatsApp. Okay? I'll immediately connect it. The other day that I was not knowing. I continue. So can you see the screen? Okay. So we are looking at what are radial functions and how the radial functions are solutions of the Laplace equation. So there are two ways we have seen. One is first verify these functions. So let me write a fresh. So step one is to verify that log r v of r is equal log r is a harmonic function in R2. That is Laplacian of v is equal to 0. This is step one. Next, in general, verify that this is 1 and v of r is equal to r power 2n minus 1, 2 minus n. Okay, this is harmonic. What is r here? R is the point x naught and take a disk. This is R, disk of radius R, and like we on the points on the these points, these points x. x is equal to, or you can call x1, x2, okay, x1, x2, any point x1, x1, x2. That is, r is modulus of x minus x general. So what we are saying is, if you take a function of r, this will be harmonic function. This is what we have seen yesterday. And in general, for any n is equal to, for n greater than or equal to 3, for in particular 3 dimensions, in 3D, 3 dimensions, 1 upon r is harmonic. Okay, if you see this, this function v of r, or this 1 by r, they are not defined at v of mod x minus x naught is not defined at x naught. Okay, they are not defined at x naught. That's what we have to see. If there's a problem at, so there is a singularity of these functions at the point x naught. That is, we know that r should be strictly radius, so r should be strictly positive. So this is the step 1. What is step 2? Step 2 is directly if we have Laplace equation, okay, when v is a function of r only, v r depends only on r, that is radial functions. Radial functions. Then what is the Laplace operator? What is the equivalent? How the Laplace equation reduces? What is the del Laplacian of u? Laplacian of u. So we have seen that yesterday. It is that if you have this thing v of r only, then how to find? It is del v upon, first find del v upon del r, that is equal to del v upon del xi, del r upon del del xi, and first find is equal to del v upon del r times del r upon del xi. Okay. Now, because we want to see what is Laplacian of v, so this is v is a function of r only, so this is v prime of r. What is del r upon del xi? It is xi upon r. Yesterday we have seen, because r is mod x, so that is you can, that is nothing but in 2 dimensions or n dimensions, 1 square plus 1 plus xi square plus 1 plus xi square. Okay. So when you differentiate r with respect to xi, this will be 1 upon 2 square root all these things into differentiate differentiation will fall on this. This is twice xi. So this is xi upon r, because this is r. Okay, that is our here we are substituting in place of del r upon del xi. Okay, now do a second derivative, del square v upon del xi square, because Laplacian of v is summation I is equal to 1 to n. This is our Laplacian of v. So do another another derivative with respect to xi, that is equal to summation I is equal to 1 to n. If you do another time, again you have this function. So product rule here, you want to differentiate this with respect to, so it will be r and one factor, and another factor is already there. Keep this fixed and differentiate this, and plus keep this xi upon r, differentiate this xi upon r. Keep the v dash, keep the v dash of r and do the differentiation. So this is r times 1 minus xi times what is that? I am doing the differentiation with respect to xi. So what is 1 by r? What is the difference? Minus 1 upon r square into xi upon r square. There is an r here also, there is an r here also. So I have to do differentiation. So this is equal to summation I is equal to 1 to n. Yeah, v double prime of r I can take out, and xi square upon r square. So this is r square plus v prime of r I can take it out, and the summation will go 1 upon and this is 1 upon r minus what is going on here, the plus, I think plus xi square is there, summation xi square will go, and r cube. This will be r square, right? R cube, and we also have r square here. So carefully here. So that r square and this r 1 by r and r cube. Yes, 1 by r. So finally, what is the answer here? Application of u. xi. Yeah. So here, if we see here, this r square, we have to be careful here. So this part is correct. So here I am doing it again. So what I am upon del xi v double prime of r in v prime when we are the differentiation of see this is the part from here we have to from here we have to differentiate again. I'm differentiating xi upon r. Okay. What is the definition? Del upon del xi of xi upon r. Okay. So this is equal to v double prime of r xi square upon r square plus v prime of r. So here do a u by v this thing differentiation. So I am doing this. This is our r square. First of all r into differentiation of xi is 1 minus xi into differentiation of this one del differentiation of xi into differentiation of r that is r upon r square. So this is one. So now here if you see this is r is cancelled here and xi square upon r is there. Okay. So now okay, let me write clearly v double prime of r xi square upon r square plus v prime of r into 1 by r minus x. Okay, is this clear? Any queries? Are we connected? Okay. Please someone respond. Is it clear up to now?
Yes, sir. Yes, sir. Yes.
Sorry, I kept my speaker. It's clear, sir. Okay, thank you. So now do the summation with I is equal to 1 to n. Now do the summation with respect to get the Laplacian of v. Okay. So that summation will fall here also, here also, here also. Okay. So that will give us v double prime of r, and this is r square. So this and this cancels, plus v prime of r. This will be n upon r minus this will be r square. So this will be 1 by r. So finally we have the Laplace, the differential Laplacian of v becomes v double prime of r plus n minus 1 times upon r v prime of r. Okay, so we can solve this now. We can solve this easily by integrating. So solve for how to solve? Just take this the other side prime of r, and now divide by this thing. Now integrate both sides. This is ln mod log mod v prime of r is equal to 1 minus n times log r plus log c. So now if you take out the logs, then it is v prime of r is equal to r power 1 minus n into a constant. Let us call this constant as c. Okay, now integrate again. V of r is equal to c2 r power 1 minus n plus 1. Sorry. This is equal to c1 plus c2 plus n. This is our VR. See here, this this is the case when n is greater than or equal to 3. What happens when n is 2? The case when n is equal to 2 is the case when n is in 2 dimensions. You look at here, n is equal to 2. N is equal to v prime of r is equal to c2 upon r. So integrate both sides. V of r is equal to c2 log r plus c. So these are the, this VR is n greater than or equal to 3. This is n is equal to. So these are our radial solutions. Radial solutions. VR is equal to C1 plus C2 log R n is equal to 2. C1 plus C2 R power 2 minus n upon 2 minus n when n greater than or equal to 3. And now from radial solutions, how to get fundamental solutions. Okay, so what is the definition of Definition of fundamental solutions. Okay. So definition: a function k of mod x is fundamental whenever integral k mod x Laplacian of v x dx over the domain subset of Rn is equal to v of c. Okay. This is the definition of fundamental solution. In any n greater than or equal to, what is kx? Yeah, this is the definition. And yeah, here now we have to prove, find. Now the final step is, that is step 3 is find C1 and C2 such that V of R, you can call it as K of mod X, is fundamental. This is what we are going to now demonstrate. Here one more thing is there. These are called test functions for all V compactly supported C2. Okay. Now we are going to do this. This is the there is a process to find the constants C1 and C2. Is it clear?
Sir, why is the radial solution or fundamental solutions?
Pardon me? Repeat again.
Why is the radial solution or fundamental?
That's what we are going to prove. These are we are going to why are radial? That is what we are going to prove, that our V functions, whatever we have obtained here, these will satisfy or find constant C1, C2 such that they satisfy this equation. Sorry, this V and this V should not be confused. So let us call, after finding this is called K of R. Forget about V now here. This V is not the same as this V. Okay. Again, I am writing now. K of mod X is equal to K of R is equal to C1 plus C2 log R, n is equal to 2 case, C1 plus C2 R power 2 minus n upon 2 minus n when n greater than 3. R is fundamental because are fundamental solutions. Fundamental. No. Find C1, C2. Find C1 and C2 such that are fundamental. That is integral K mod X Laplacian of v of x dx on the domain omega is equal to v of 0 for all test functions v belongs to compactly supported C2 of R, or C2 of omega. We are going to make these functions. First, we have found the radial functions. We are making them fundamental by finding the constants C1 and C2. Okay. By finding the constant C. That is the process. I am doing that process now. Because V is compactly supported, because V is compactly supported, that is if you we are in Rn, so there is a domain omega. What is meant by compactly supported? That means you can if there is origin, you can always find a R radius such that what is the meaning of, because it is compactly supported, that is we can find an R positive real number such that V of x V of x, V of x identically 0 for all x belongs x greater than for all x mod x greater than or equal to R. Outside the ball, including the boundary, this is equal to 0. We can find an R positive such that compactly supported means it is the finite domain. It has a finite support where it is on the finite domain. Also, you can, yeah. So what will so that means we can this ball is called B R 0. Ball centered at the origin and radius R. Okay. So domain is this thing. So now let me call this as omega. Call omega as, take omega as VR. And kx has problem at the origin. Kx has a problem at the origin. So we are like this situation. This is R. This is origin. So take an epsilon. Take an epsilon. This is V epsilon 0. So now take the annular region. Now take omega epsilon is equal to V, that is omega minus V epsilon 0. So on omega epsilon, K of mod x is smooth. Okay, there is no singularity. Now we can apply Green's identity. Recall what is Green's identity? Recall. we call Green's identity. That is, if you have two functions u and v, c2 of omega, okay, then what is the Green's identity saying? So it is something to do with the integral on the domain is equal to integral on the boundary. Okay. So how did we get this? We used um, divergence theorem. Divergence theorem has something like f bar um, f bar dot, that will be here, f bar dot n cap, yes, and here divergence of f bar. So take f bar as v grad u. Sorry, v grad u. This is a vector. V grad is what? Del u upon del x1, so on del u upon del x. Okay. So what is divergence of this? That is del dot del dot f bar. This will be v Laplacian of u. Okay. And f bar dot n cap will be f bar dot product with the n cap. So that will be v del u upon del nu. Okay, the radial the outward normal vector. Okay, grad u dot n cap will be, or you can say it is n cap. Okay, this is our grad u dot n cap. It is nothing but the directional derivative in the direction of the outward normal nu. You can call it as. So now put this del this here and put this divergence here. Then we have the Green's identity. Green's identity as integral over the domain v Laplacian of u is equal to integral over the boundary v del u upon. Is it correct? Where is the, yeah. So go back to our page. See the notes on the Green's identity. So here is the Green's identity. Yeah. So yeah, there is a product rule here. Yeah. So this is the mistake. So we have v Laplacian of u plus grad v grad u. Yeah. So when we do the yeah, here we have grad v grad u. one dot falls on here and another is here. Okay, this is two functions. So here we have v Laplacian of u plus grad v. Okay, is it clear?
Yes, sir.
Thank you. So now apply the Green's identity. This is our Green's identity for the functions k of x, k of mod x, and the test function v of x. Okay. So what should be our take in the Green's identity? This should be our k. And k is a function. Yeah, we what should yeah, and what should be the domain here? Wherever it is. Now come to our here. So if you see this one, Green's identity, yeah, Laplacian of v on the this thing on is equal to the boundary is it has two parts. So write this thing properly. Green's identity. Green's identity is this. So grad v. So from here, how we got this is our Green's identity here. So and we yeah. Here is a trick. What is that? Yeah, I'm writing here. So come back here. So if I interchange this function, so one identity is integral over omega. V is our k. Yeah. V Laplacian of u is equal to so plus grad v grad u dx is equal to integral v del u upon del u. Suppose now I have interchanged v and u. What is the second identity? Integral over omega u Laplacian of v plus again grad u grad v dot product dx is equal to integral u. I can change the functions. Now subtract from one another. 2 minus 1 implies integral u Laplacian of v minus v Laplacian of u dx omega is equal to integral on the boundary of omega. This 2 minus 1 u del v del u minus v del u This is what is green. So this is another form of the Green's identity. So now apply K of and V. Then what will happen? Del Laplace of K. These are real functions. K's are so in 3. Put U is equal to K of mod X. Are we back? Are we back again?
Yes, sir.
Yes.
Yes, now, where did we where it disconnected? Is it okay? This one, 2 minus 1.
Yes, sir.
Okay. So now we got the final thing. Laplacian of K is 0. So integral K of mod X Laplacian of V on omega is equal to, in fact, on omega epsilon we are doing, is equal to integral on the, this term has gone 0 because Laplacian of K is 0. We are putting U is equal to K and V is equal to V. So U is equal to K. We on the K LU minus E times del K. Okay. Now, what is the boundary of? See, we are like this. Our omega is, this is R, this is epsilon. So this ball is BR at 0. This ball is B epsilon at 0. This is our omega. So boundary of omega epsilon is this angular region, this region. So what is the boundary? Boundary is boundary of BR union boundary of B epsilon. Okay. So now this boundary of omega epsilon will divide into two integrals. So the right hand side. So this will be integral omega epsilon K Laplacian of V dx is equal to. So we have two boundaries. On BR, V is 0. So this part is 0. So only thing we'll have is boundary epsilon K mod X del V upon del V. Okay. only this will remain, because if you this, minus v x del k del u x. This will also remain, but del on this boundary, what is BR? BR is boundary R is mod x is equal to R. On mod x is equal to R, V is identically 0. So V is 0. So del V is 0. V is also 0. So this boundary will not come. Only this part will come. So now what is now what is K of x? K of x is C1 plus C2 log epsilon, that is n is equal to 2 Ks, and here it is a boundary, so points x mod x is equal to epsilon here on this boundary. Okay, and also find and C1 plus C2 epsilon power 2 minus n upon 2 minus n when n greater than or equal to. This is our K of epsilon. This is the K of epsilon. What is del K of del nu at epsilon? Mod x is equal to epsilon. This boundary is nothing but mod x is equal to epsilon. Find the normal derivative, outward normal derivative. So we have situation like this. So this is the boundary of V epsilon. So instead of outward normal, we can take negative of inward normal. That is radial this thing, and just do the derivative with respect to epsilon. That is equal to C2 C2 upon epsilon, n is equal to 2 Ks, and C2 what is the derivative of this? Sin n into epsilon power 2 minus n minus 1. So 1 minus n. This 2 minus n will cancel. So substitute back this thing and this thing in the here and here. Then final step is 10 mod epsilon, let epsilon goes to epsilon. So what will happen finally is C2 and C2 C2 can be. So we'll do this in the next class. We'll complete this part, or if you can also see, it will be easier for complete this left out. Here we have computed correctly the C2 upon epsilon. And these will go to 0. If you have any queries, please ask. No exam today. No exam. Any queries? Anirudh is asking something. Please unmute. Anybody is asking any queries? Anirudh, are you asking anything? Please unmute. So if you have no questions, we'll log out. Thank you.
Thank you, sir.